Okay, hello everyone. My name is Adit Jain and today I'll be explaining balance modulators. This is part of my Principles of Communication course assignment, but I'll be trying to keeping a general perspective. Let's just start. So for balance, balance modulators are of two types. One, the ideal balance modulator, and the other, the physical implementation of a balance modulator, which is called a double balance modulator or a ring modulator. Uh, this is how a balance modulator looks like, and this is how a ring modulator looks like. Well, I know after seeing the circuits you must be very scared, right? And you must be so because these are a lot to take in, definitely a lot to take in. But also, let's just dive in. Before diving into what they are, let's just dive into why do we need them in the first place. So we need them to generate the double sideband suppressed carrier modulation. A very big term. Let's try to break it down. Let's see what this modulation is. So basically we have a modulating signal. Let's just take y is equal to x for now, and we have a carrier signal which is basically say a sine wave or cosine wave. So when we multiply them, what we get is a double sideband suppressed carrier modulation. So we have simply multiplied them, and this is how the the blue one is how the multiplied version looks like. Y of t is equal to ac cos 2 pi f ct, which is basically c of t and m of into m of t. So now you can see that it is the carrier wave which is being enveloped by the modulating signal. Okay, let's look at the Fourier transform representation of this. So simply the Fourier transform of the modulating signal uh, looks something like this, because this is a finite signal and it is not an infinite signal. So this is how it looks, and this is how the Fourier transform. So orange one is the Fourier transform of the carrier wave. So this is basically an impulse because it is a sine wave, and the y of t is basically so y of t is the output, and this is how the Fourier transform of the output looks. Let's just zoom in here. So once we zoom in here, what we see is the blue one was the y of t, and so there is no carrier component in the y of t, which is why we have the term carrier suppression, and there is an identical sideband on both sides, which is why we have double sideband. So double sideband carrier suppression modulation looks something like this. Why do we need this? We need this so that we can have maximum amount of power transfer in of the modulating signal itself, and less power transfer of the c of t, so when start traveling the wave. But how do we generate these double sideband carrier suppressed modulation? So that is where this balance modulator that we earlier looked at comes into picture. So this is how a balance modulator looks like. Let's try to understand its functioning. So to get a feel of its functioning, what we can see is that we have a modulating signal which is being modulated by a carrier wave, and a negative of the modulating signal which is again being modulated by the carrier wave or carrier signal. Then these two signals are being added, and the negative of this particular signal has been added to get the output signal. What would this mathematically mean, and why is this called balanced? We'll look that into a little bit later. But yeah, you can see when we add both of them, so this is when I modulate m of t, and this is when I modulate minus m of t, and I subtract it. So what I get is that s of t is nothing but some constant into m of t into c of t. So that is, and I can obviously amplify it or de-amplify it to get or attenuate it to get my same signal that I earlier looked upon, which was this particular signal. Well, m of t is a specific case here, but m of t can be anything. But to get a practical realization of this, so how do I practically realize this particular equation? That is where the ring modulator comes into picture. So the ring modulator is nothing but this particular circuit. So let's just try to break it down quickly. So m of t has been transformed here, and there's a c of t across these two terminals. Right now it is in the midpoint and it has been balanced. Balanced as in that there's no potential difference between any two parallel parallel points of these two particular edges, and so there's no potential component of c of t between these two edges. Okay, so when c of t is positive, you can see that these diode AB and this particular diode is active, but when it is negative, this particular diode is active or on, and these are off, and these are off when this is positive c of t. So once c of t is positive, since only these two diodes are on, m of t is simply transformed, is simply present here, and s of t is nothing but m of t. But when it is c of t is negative, these two diodes are on and that leads us to having a inverted m of t, and s of t is equal to minus m of t. Let's again look at what this looks like mathematically. So this is how it looks mathematically. So we have nothing but s of t is equal to sigma t m of t. So sigma t, and where sigma t is 1 when c of t is greater than 0 and minus 1 when c of t is less than 0. So that is how our s of t, or the output function, looks like. Now focusing on especially on the c of t, we want c of t to be a square wave. So how does a square wave look? Well, the square wave looks something like this. So this is the square wave, and as you can see, the square wave in itself has a Fourier series representation, which we know looks something like this, where this is the Fourier series coefficient 4 by pi into minus 1 n minus 1 to n minus 1, and the Fourier series representation of it looks something like this, right? So this is a carrier wave, so orange one. So these coefficients decrease as we go down the lane, and once we multiply this, so this is the carrier square wave, and since this is being so the output wave looks something like this, because we know it is plus 1 when that is there, and minus 1 when so sigma is present here. So I can just directly go here. Sigma is something like this, and since sigma depends directly on c of t, and c of t is periodic in nature, sigma will be periodic in nature, and hence we have our conclusion. Okay, so this is how our output wave looks like. So this is the Fourier series representation into m of t. Okay, now before we go into the question why this is a balanced oscillator, let's have a quick look at how do the waves look like in the ring oscillator. So we have two waves. We have a square wave and we have a modulating sine wave. So basically the output is nothing but the square wave being enveloped by the modulating sine wave. This is how the output looks like. So this is a very funny shape, and actually a very interesting shape. So m of t is basically nothing but m of t is a sine wave, so it will have two components and two impulses in their Fourier transform, and c of t will have infinite number of Fourier series coefficients, but they are decreasing, so the other ones really don't matter, but you can see them if you like. But what I want to focus on is this particular area, so let's just zoom in on that. Once you zoom in on that, what you see is that, well, this is orange one is the c of t, and there is no carrier component present in the output wave. So that is why it is carrier suppressed, and again the sideband is very symmetrical here. So with respect to the sideband also is very symmetrical, and since there is no carrier component, it is also symmetrical with respect to the carrier component. So this is why double sideband, carrier suppressed modulation, and that is how you that is one of the reasons why I call it balanced. Other reason is actually a schematic reason of why we call it a balanced modulator. Okay, sorry, I just mentioned that it is a balanced oscillator in the slide, but I meant to say balanced modulator. Please mind me. Again, so okay, I paused the recording to change that. Okay, anyways, so we have this balanced modulator because the c of t in a very balanced fashion modulates the m of t and is modulated with a minus m of t, and then is added together. So that is why, as you can see, in the mathematical equation also, the addition results in cancelling the c of t very symmetrically. So a cos 2 pi f ct minus a cos 2 pi f ct, and in a similar fashion the c of t is balanced here also in a physical manner, because since we are assuming that it is a midpoint and all things are ideal, the transformers, the diodes, therefore the potential difference between any two points will be equal, and hence it will be 0. So potential at any point should be equal and the potential difference will be 0. So that is why it is called balanced modulator. But what happens if the diodes are not ideal or anything else, or even in the case of mathematically expressing it, the ideal balanced modulator, you can see if the addition is not very symmetrical in nature, if there is a coefficient of alpha, this seeps it. So this component is 5 because it's a constant multiply m of t multiplied by c of t that can be amplified. But we have an additional component of the frequency itself. So how does this look in the frequency domain or in the practical practical ring modulator? So you can see, if I simply add an alpha of 0.5 and I add it to the carrier wave, what I see is that it is no longer being enveloped by the modulating signal and it has gone out of bonds. And similarly in the frequency domain, what I see is when I zoom it in, that it does have a carrier component or the carrier wave frequency component present in the frequency of the output. So that is why this imbalance is caused, and this imbalance can hence, this transmitting this. So some energy is spent in transferring this carrier component. Why would this imbalance happen? Well, there can be imperfections in the transformers and the diodes. There can be noise in the carrier or the modulating signal, which can lead to erroneous results. Okay. What are some ways that we can overcome these? We can introduce opposing imbalance, either a variable capacitor or a resistor in the path of the signal. So that is how we can overcome these. I would like to end this with this particular meme, that a balance modulator helps us to obtain a balance in the sense that it helps us to get rid of the carrier frequency component, and it is how things should have been. So to summarize, we looked upon what a double sideband suppressed carrier modulation is, what is a balance modulator, what is a practical implementation of a balance modulator, also known as a ring modulator, and what is an imbalance, how can the imbalance be reduced, how does an imbalance look in the ring modulator. We also looked at some graphs and some actual signals. So that's all. Thank you, and I hope I tried to explain it. Sorry for it being too long.